Alright, in this video I will be showing you how to fit data from our GitHub site to the Anton equation. So first thing we need to do is, what is the Anton equation? Well, the equation is log base 10 of the pressure equals constant A minus a constant B over constant C plus the temperature. So this is the Anton equation, and it relates the vapor pressure of a substance, of a pure substance, to its temperature. So using this equation, we can find the vapor pressure of any pure substance at any temperature. So these A, B, and C, they are constants, and how the values for each of them are made is a combination of experimental and theoretical data. So this relationship is based off the Clausius-Clapeyron relationship, and it's really useful in a bunch of different engineering applications. So let's get started. First, we need our data, right? So we need to download the file, so wget, and then we need the file URL. So here we go to the GitHub site. This is the raw data, because if you download the other one, you get a bunch of the HTML things, and it's not going to work the way we want it to. So you're going to come back here, click the link, shift enter, and run it. Everything went nicely. So now we have it downloaded. Next, we need to assign it to a variable in our code. So we'll call our variable data, and to do this, we need to use numpy. So let's import that. Import numpy as np, and now our variable data will be set to, we use numpy load text to get the file, and the file name. So water vapor pressure .csv. The file name's right here. So I just type that in quotes and shift enter. Run, see what happens. Well, we got an error. So the error is it's trying to convert this value into one number. And if we go back and look at our data, this is the first line. It is 2 data points and they're separated by a column. So we have to tell load text that our data points are separated by a comma. So to do that, it has a parameter delimiter, and we will set that to our delimiter, which is the comma in this case. So now it should run nicely, which it did not. Let's see. Oh, I need a comma. Now it'll run nicely, and if we go and look at our data, there it is, our array with our data. So looking at the numbers, I could tell the first column is all temperature data, because it's all in it's like 293, 303, 313, that's temperature. So the second column must be our pressure. So from here, we can do data, or our pressure is going to equal the data, everything in or all rows, and everything in that first column, which is index 0. Our temperature is going to be, oh, I'm doing this backwards, what am I doing? This is the temperature data, it's everything in the first column. And then the pressure data is everything in data, all rows, and the second column. So run that, now we have our temperature and pressure. But if we think back about the Anton equation, it is log base 10 of the pressure plotted against temperature. So let's make another variable. We'll call it the log 10 of P. And it will just be, we'll take the log base 10 of our pressure using numpy. Numpy log 10 of our pressure. And that is what we'll use to graph our data. So let's go ahead and do that. First, we're going to need to import plotly. So from plotly dot subplots, import subplots, yep, spell that right, import make subplots. And then we'll also import plotly.io as BIO and use it to make the default background dark, because it's easier to look at. Templates.default equals plotly duck. Alright, let's see if I typed everything right. Now we have an issue. Let's see. I missed the L here. And we also have an issue with this. So plotly dot subplots. There we go. Subplots equals make subplots. Another issue still. Plotly dot subplots make subplots. I'm just missing L's and everything today. Alright, there we go. So now we can use plotly. Now that I actually got it imported correctly, let's use it to plot this data. So our data will be figure 1 equals make subplots. And then figure 1 add scatter. Figure 1 dot add scatter. And our x values are the temperature, and our y values are the log-based time of the pressure. So there's our data. Let's do it as data points. So let's switch the mode to markers, so that'll plot as individual points and not a line. That's a little more useful for looking at this data. So here it is. Now we have our data plotted. Now we need to fit a line to it. So we're using nonlinear regression. So we need to get the sum squared error, right? That'll be, so let's make our function, sum squared error, and we'll pass our unknowns as a vector to it. So what the sum squared error is going to do is it's going to take a line, since we'll pass it A, B, and C, so it'll be using the Antione equation to make a line, and it's going to change, and it's going to add up all the values, the differences of the squares, sum squared error, and we'll use that. Once that's minimized, we will use it to plot our data. So we'll need the difference, so it needs to return the difference between our actual data and our theoretical data. So our theoretical data is our model, so A minus B over C plus T, minus our actual data, which is our log 10 of P variable, because it's the log base 10 of pressure, right? And that'll give us the difference. And if we just leave it like this, we'll have negative and positive values, because a positive deviation won't be counted the same as a negative deviation. So in order to make that happen, we'll square it, and then we need to sum it up. So there's our square error. Let's use numpy and make it the sum squared error. So now it's underlining A, B, and C because we haven't defined those. That is just going to be the vector that we pass to our sum squared error function. So A, B, and C, they'll be equal to V. Let's run that, make sure everything's okay with that, no typos. And our goal is to minimize this, because if there's no error between our line and our data points, we have a line of best fit. So to do this, we're going to use minimize from SciPy optimize. Come back up to our import statements. Import SciPy from SciPy optimize. Import minimize. All right, make sure to run that. Run everything down again, and we'll go minimize our function, which is our sum squared error. And we need to give it a guess. We're passing 3 values, A, B, and C, so that needs to be in our guess for it to work. So I'll just guess 1, 2, and 3, and we'll run that. We'll try again. I need to spell minimize right, and we'll run it. Okay, and so here it is. The message says it terminated successfully, so our guess was close enough that the program was able to run right. And here is our answers. A, B, and C. So we don't need all of this, right? Minimize outputs a lot of different attributes. We just need the X attribute down here, because that'll just give us this array. And We could set it to another array, but I'm just going to unpack it since we know those values will be A, B, and C. So now we have A, B, and C. Let's plot our line of best fit. So we'll do figure 1, add, scatter. Our x is still temperature, and our y will be our model. So A minus B over C plus temperature. Let's see how this looks. And there you go, pretty good, lines up, but you'll notice that in between the data points where there's a big separation, it just connects it with a straight line. We don't want that. It's not the best for finding the data points inside between these 2 points. So we will fix that by giving it more temperature points to plot towards. So we'll come back up here to our datum, and we will do tplot equals, we'll do we'll use numpy linspace to create an even amount of data points between our temperature values. So our lowest one, 293, we'll go 280 to up to 650. So our start is 280, our stop is 650, and let's say 200 data points. Put it nice, and then we'll run this, and then we need to come back down here. Instead of plotting it to T, let's use our tplot and change it in our model as well. Tplot, and run it. Helps if I spell tplot right, and we'll run that, and see, there, the line fits a lot better. So that is how you fit our data to the Antione equation using nonlinear regression. So now I'm going to show you how to use linear optimization on the Antione equation. So before we go into Python and code that, we need to manipulate the Antione equation a little bit because it's not linear, right? We have our variable c in the denominator, and we need to change a few things before we can set up our design matrix and go into coding. So my first step is to multiply both sides by c plus t to get our variable out of the denominator. So this will give us c times log base 10 of pressure plus temperature times log base 10 of pressure equals A times C plus A times T minus B. Now I'm going to reorganize this equation. I'm going to move all of our unknowns to one side and our knowns to the other side and split it up so I can create the design matrix. So on this side we'll have A times T minus, we'll move this term, C log base 10 of P over, so it'll be minus C log base 10 of pressure plus A C minus B, and this equals T, our temperature, times the log base 10 of our pressure. So now from here, we can create our design matrix, our matrix of variables, and our solution. So I'm going to start on this side. This one's easy. The only thing on the right side of the equation is just T times log base 10 of P. So in here, we'll have T times T1 times log base 10 of P1, our first pressure. Same thing with our second term. It'll be T2 log base 10 of P2 all the way down to our nth term of pressure times the log base 10, or our nth term of temperature times log base 10 of the nth term of our pressure. Now, let's create the design matrix. So, how I like to think about it is we'll have the first column times our first variable. We'll make a term here. Second column times the second variable will make a term, and so on. So, if we look at it, our first term is A times T. So, our variable A will be multiplied by T. So, in this column, we'll just have T1, T2, all the way down to Tn. So now when we go to do matrix multiplication, we get T times A. So now we need the second column times a second variable. So if we look, we have c times negative log 10 base of p. So we'll have c here, and then negative log base 10 of p1, negative log base 10 of p2, all the way down until our nth term, negative log base 10 of our nth term of pressure, right? And so our last two terms on this side is a times c and minus b. So those are all variables, so we can't set them up the same way that we did these other two, because they're all unknowns, right? And so what I'm going to do to solve this problem is just call that whole equation d. So we'll put d down here, and now we need something in this column times d to make d. Well, we'll just put 1. So this will just be a column of ones. And there we have our design matrix. Now we can go into Python and code and get our line of best fit. All right, now that we have kind of changed the Antione equation a little bit and got it into a form that we can use linear optimization on, let's do it using Python. So similar to nonlinear, we need to start by getting, downloading the file and opening it up so we can actually use it. So again, we'll use wget, and we'll come over to the GitHub site. Remember to click raw data so that it's easier to use. Get this link. We will copy it over into our code, and we'll run this first line, right? So it kind of it downloaded in, so that looks all good. So now let's start our code. We'll start by importing numpy as np, and then we will call our data, variable data, pretty simple. And we'll use, again, the numpy function load text to water vapor pressure to load in our data into our variable. Remember, we need to include the delimiter so that it works. And in this case, it equals a comma. All right, we'll run that, make sure everything goes good. Data, all looks good. All right, from here, we will now get our temperature and pressure data. So our temperature is the first column in data, so all rows, and 0, which is the first column. Our pressure is the second column, so again, all rows, and the second column, index of 1. And then I'm also going to go ahead and make our log 10p of data so that we can graph it and kind of see it again as we do our linear optimization. So log 10 of p will equal numpy log base 10 of p. And let's run all that, make sure it all checks out. So now that we have our temperature, pressure, and our log base 10 of pressure data, we can import everything we need to graph the to graph our data. So first, let's import plotly subplots. And then I'm also going to import plotly.io so we can again change the background, makes it a little easier to look at, especially when I have the dark background for my collaboratory. So as PIO, and then PIO.templates.default, we'll set that equal to plotly dark. All right, make sure to run this again, and now let's create our figure. So figure 1 dot make subplots. So equals figure 1 equals make subplots. Almost made that issue. Make subplots, and then we'll do figure 1 dot add scatter. And in this case, our x will be our temperature data, our y will be log 10 of p data, and we'll make the mode markers so it comes up as data points and not a line. So there we go, we'll run that, and here's our data. So from here, we can now start to use linear optimization and get our line of fit. So in the portion where I did it on the whiteboard, we figured out that our design matrix is 3 columns. So we'll start by we'll call our design matrix Z, and we'll use the numpy function, numpy.c underscore. This makes columns. So our first column is our temperature data. Our second column is going to be negative log 10 of P. And the third column is just a column of ones. So to create this, we'll do np dot ones like, so numpy1 like, ones like, and we'll make a matrix of ones like temperature. That way the dimensions match up and it's right. So let's run that. And we get an error. Let's see. Oh, I do this all the time. I need to remember to use square brackets when I use this function. So there, now it works. And so now that we have our design matrix, we can solve our equation that we made and get the values for A, B, and C. So to do this, we'll use numpy.linearalgebra.solve. On the left side of the equation, we'll have transpose of our design matrix multiplied by our design matrix. Remember to use matrix multiplication. And then the right side of our equation will be, again, transpose of our design matrix times T times log 10 of P. Okay, and then let's see, make sure everything checks out for there, and there's our solution. So if you remember, we solved for A, B, and D because the way the equation was set up, we couldn't just straight up solve for C. So let's set this equal to A, B, and D, and then we will solve for A, C, and D, and then we will solve for B. So B is going to be equal to A times C minus D. All right, run that up. So now that we have A, B, and C, we can plot our line. So we'll do, actually before I do this, let's create a set of temperatures to plot our model against. That way it's kind of a smoother curve. Same thing as we did in nonlinear optimization. So we'll call it tplot equals numpy linspace from 280 to 650, and we'll do 200 data points. Run this. Now we can graph it. So we'll do figure 1 dot add scatter. Our x data is tplot. Our y data is our model. So now that we have A, B, and C, we can make our model, which is A minus B over C plus tplot. And let's see how that looks. And there we go. There's the line fitted to our data using linear optimization.